Good morning to everyone. See, in the last lecture of analog and digital electronics, we have started with typical applications of operational amplifiers. Okay, so we have seen that amplifier can be operated in two modes: open loop mode and closed loop mode. But open loop mode is rarely used because it will offer you very high amount of gain. So practically, if we talk about the output voltage, then our output voltage is going to saturate between the positive maximum and negative maximum. Okay, so irrespective of the shape of the input voltage, you will always get the square wave as an output voltage. Okay, so we can use this open loop configuration in order to generate the square wave of certain magnitude. But there is a need to control the gain of the amplifier, and this is the reason why we are providing some feedback. Okay, so we can use our operational amplifier in two types of feedback. One is the negative feedback, another one is the positive feedback. Okay, so negative feedback is when we are providing the feedback to this inverting terminal of the amplifier, and whenever we are providing the feedback to non-inverting terminal of the amplifier, it is called positive feedback. Okay, so there are certain advantages which is being offered by the negative feedback, and this is the reason why we will we will use negative feedback operational amplifier. Okay, and that will give us the linear applications of amplifier. What do you mean by linear applications of amplifier? With the change in input, output changes linearly. Okay, so in the first part, in this module, we are going to see some linear applications of amplifier. Number of applications are there, and we'll see each and every applications one by one. So in the last lecture, we already have gone through the ideal inverting amplifier. Okay, so this is the typical circuit used to represent ideal inverting amplifier. Now what we have seen in this particular case is we are providing some supply voltage to this inverting terminal, and you can see the non-inverting terminal is grounded. Okay, now before we start analyzing any amplifier circuit, we have two realistic assumptions. What are these two assumptions? The assumption number one is we will consider the current input current to amplifier is equal to 0. Okay, and second assumption was the concept of virtual ground. Okay, so the concept of virtual ground says that whatever potential is available at terminal A, same potential will be available at terminal 2. Okay, so this is what we have seen. Now here, if we look at this terminal B, it is grounded. So definitely we know that ground B is at zero potential, and according to virtual concept, ground terminal A will also be at zero potential. Okay, so if we talk about VA, then VA will be equal to 0 because VB is at 0, right? So now this is our realistic assumptions, and based on these assumptions, the current IB here will be equal to 0, right? So whatever amount of current will start flowing from the supply voltage, this entire amount of current will flow in this particular direction, as you can see. Okay, let us say this current is I. Okay, so now certain magnitude of current I is flowing from V in terminal to A terminal. Okay, and this current is nothing but V in minus VA by R1. That is what we have seen, right? So I is equal to V in minus VA by R1. That is what we have seen, but VA we know, VA is equal to 0. So this current is V in by R1. Similarly, if we look at this output side, okay, there is also one current flowing to this feedback resistance RF. Okay, so if we talk about the magnitude of current I from terminal A to output terminal, then I is equal to VA minus V0 divided by RF. Okay, so I is equal to VA minus V0 divided by RF. But as we know, this VA is at zero potential. So my value of current will be minus V0 by Rf. Okay, but all these two currents, both these currents are same. Okay, so we can compare these two current. V in by R1 is equal to minus V0 by Rf. Okay, from this equation, if you find out the value of V0, then V0 is equal to minus Rf by R1 times V in. Okay, so this is the output voltage equation. Now here what we have seen is this ratio Rf by R1 is nothing but the gain of the closed loop configuration. Okay, so now by changing these values of Rf and R1, we will be able to control the closed loop gain of the amplifier. Okay. So now it is up to us by how much amount we want to amplify our input signal, and accordingly we will select the proper values of this feedback resistance and R1. Okay, and this negative sign indicates that my output voltage will be opposite to that of input voltage. Okay, so suppose this sinusoidal waveform represents the input signal, then in this case the output voltage will be 180-degree out of phase with respect to input voltage. So the output voltage will have a shape of this voltage. Okay, magnitude will depend on the amount of gain provided by the typical circuit. Okay, so this was the inverting amplifier, right? Rf by R1 is gain of the amplifier, and negative sign indicates that the polarity of output is opposite to that of input, and this is the reason why this amplifier circuit is known as inverting amplifier. It will invert the actual voltage, right? Now today we will see one more circuit. Suppose I am providing the input signal V in to this non-inverting terminal. Okay, at that time what should happen? What will be the output voltage? What should be the gain in that particular case? Okay, so this configuration is known as non-inverting amplifier. Whenever we are providing signal voltage, supply voltage to non-inverting terminal of the amplifier, we can say that we are available with non-inverting amplifier configuration. Okay, and this is the reason, this is the circuit which represents non-inverting amplifier. Okay, we are talking about the ideal case only. So ideal non-inverting amplifier. Okay, so now an amplifier which amplifies the input without producing any phase shift between input and output is called non-inverting amplifier. Okay, so this circuit, what it will do, it will produce, it will amplify, it will amplify input without producing any phase shift between input and output, between input and output. Okay, so this configuration is known as non-inverting amplifier. Now what is the difference between the previous circuit and this circuit? As you can see, non-inverting amplifier is connected with the source of supply voltage V in. Okay, this is my terminal B, and terminal A is grounded. Okay, this inverting terminal is grounded. Now what will happen to this circuit diagram? Let us try to understand. See, whenever I switch on the supply, what will happen? The input current, as we have discussed, is equal to 0. Okay, and here no supply voltage is there, so at the output side we will get certain supply voltage, and the current which is producing is given as feedback current in this particular direction. Okay, so this current will come over here, okay, and it will follow in this particular direction. Okay, now there is two possibilities at this terminal A. Some part of current may flow in this direction and some part of current may flow in this particular direction, but as per our realistic assumption, current toward operational amplifier is equal to 0. Okay, so entire amount of current I will flow in this particular direction only. Okay, so from output terminal through feedback resistor through terminal A through R1 resistor, the entire current will be grounded, causing a voltage drop across these two resistances. Okay, now the question is, this is the amplifier circuit. So by what amount we have amplified our input signal? Okay, so we are interested in deriving the gain of this amplifier. Okay, so let us try to derive closed loop gain. Okay, so we'll see derivation of closed loop gain. Okay, now here if we talk about this node B is at potential V in. Okay, so what will be the potential of node A? Definitely same as node B. Okay, so VA will be equal to VB will be equal to VC. Okay, and this is from the concept of virtual short. Okay, so from the concept of virtual short, we have VA which is equal to VB and that is equal to V in. Okay, let us call this equation as equation number 1. Okay, now because of this supply voltage V in, there is a production of current I which is flowing in this particular direction. Okay, so consider the output side of the equation. This current I is flowing from this terminal to terminal A. Okay, so the current flowing between these two terminals is, okay, we'll consider the output side. Okay, from the output side we can write I is equal to V0 minus VA divided by RF. Okay, now what is VA? VA is equal to V in. Okay, so we have V0 minus V in divided by RF. Let us call this equation as equation number 2. Okay, and at this inverting terminal, now current I is flowing from VA to ground. Okay, so at the inverting terminal, I is equal to VA minus ground, that is 0 potential, divided by R1. Okay, what is VA? VA is equal to V in divided by R1. Call it equation number 3. Okay, so you can see the entire current passes through R1 as the input current of op amp is equal to 0. Okay, so the magnitude of equation number 2 and equation number 3 are same. Both the currents are I. So we can equate these two equations. Okay, so equating equation 2 and 3, we will be able to write V0 minus V in divided by RF is equal to V in divided by R1. Okay, now what we are trying to do with this analysis, we are trying to derive the closed loop gain. Okay, and whenever we talk about the gain, remember gain is nothing but the ratio of output by input. Okay, so what is output in our case? Output is output voltage V0. And what is the input? Input is supply voltage V in. Okay, so we'll try to find out this ratio V0 by V in, and that will give us the value of gain. Okay, so let us separate these two out. Okay, V0 by RF, okay, is equal to V in by R1, and this V in by RF is negative on the left hand side, so it will become positive. So positive V in by RF. Okay, so here V in is common, right? So let us take V in as a common factor. It will become R1 plus RF divided by R1 RF. And let us take this V in on the left hand side of the equation. So we have V0 by V in is equal to R1 plus R1 plus RF into RF divided by R1 times RF. Okay, so this RF will get cancelled out. RF will get cancelled out, and we will be left with R1 plus RF divided by R1. Okay, so this is our ratio. Okay, the ratio V0 by V in is equal to R1 by R1 plus RF by R1. So R1 by R1 will be 1 plus RF by R1. Okay, what is it? This is the closed loop gain. Okay, so now my closed loop gain in case of non-inverting amplifier is 1 plus RF by R1. Okay, and if we talk about the magnitude of output voltage V0, it is equal to 1 plus RF by R1 into V in. Okay, so we can see with the help of this amplifier circuit, we will be able to amplify the signal how much times? 1 plus RF by R1 times. Okay, and you can see here the output voltage shows a positive sign. Okay, this positive sign indicates that there is no phase shift between this input and output. Okay, so output voltage waveform and input voltage waveform both will be in phase with each other. Okay, so suppose we have applied some sinusoidal source of certain amount of voltage like this. Okay, then in that case the output voltage will follow the waveform of input voltage, but magnitude will be increased. Okay, so this will be the output voltage waveform. Okay, it indicates V0, and the purple waveform indicates V in. Okay, so these are the waveforms of non-inverting amplifier. Okay, so now we have gone through inverting amplifier, we have gone through non-inverting amplifier. Okay, we can see the gain in case of inverting amplifier is minus RF by R1, and gain in this case is 1 plus RF by R1. Okay, let us try to compare. Okay, so on the one side I will consider ideal inverting amplifier, and on the other side let us consider ideal non-inverting amplifier, right? So if we talk about the gain of voltage gain will be equal to minus RF by R1, right? And in case of inverting non-inverting amplifier, it is 1 plus RF by R1. Okay, this is the first comparison. Second one is output is inverted with respect to input. In this case, output is inverted with respect to input, while in case of non-inverting amplifier we have seen no phase shift. Okay, so no phase shift between input and output. Okay, so here in case of inverting amplifier, the voltage gain can be adjusted as greater than or equal to or less than 1. Okay, if I talk about the voltage gain, this is most important. Voltage gain can be adjusted as greater than equal to or less than 1. Okay, this is 1, 2, 3. But here if we talk about the voltage gain will always greater than 1, is always greater than 1. Okay, so this is the typical comparison between these two configurations, right? Now we have certain important points that can be derived from these two configuration. The first one is voltage gain is always greater than 1. Second is voltage gain is positive, which indicates that for AC input the output and input are in phase, while for DC input output polarity is same as that of input. Okay, then voltage gain is independent of open loop gain of op amp but depends only on the two resistance values. Okay, so the desired voltage gain can be obtained by selecting proper values of feedback resistance RF and R1. Okay, so this is the thing. Now talking about this non-inverting amplifier, see what I have done is I am providing the input signal to this non-inverting terminal. Okay, by keeping this resistance R1 and RF as it is in case of inverting amplifier. Okay, but this is not true each and every time. Sometimes what will happen, I will use one voltage divider network at these two input. Okay, so every time it will not be there that VB is always equal to V in. Sometimes this is not happening. And what happens when this thing is done? See, right now I am drawing a non-inverting amplifier with some other configuration. Say this is R1, this is my feedback resistance over here, and we are measuring output voltage, right? This terminal is grounded. Now what I am doing, see, I am providing the supply voltage to inverting amplifier like this. Okay, this is my V in, this is R1, this is RF, R3 and R2 are there. Okay, so here this is terminal B and this is terminal A. Okay, it is also non-inverting configuration. And what should be the output? Output voltage V0 should be 1 plus RF by R1 times VB. Why? Because the amplifier will amplify the input signal which is available at this terminal B. Okay, and this terminal B is not equal to V in, as you can see. Okay, so now you need to understand this. V in is directly applied in previous case. Okay, here V in is directly applied to terminal B, but here V in is applied through some resistive circuit. Okay, and this is the difference. Okay, here we are applying V in applied through resistive circuit. Okay, so we need to consider this. Okay, so now according to our understanding, what should be the V0? V0 is equal to 1 plus Rf by R1 times Vb. Okay, which is not equal to 1 plus Rf by R1 times V in. Okay, this is the difference between the previous non-inverting amplifier and present non-inverting amplifier. Okay, so now in this case you need to find out the potential which is available at terminal B, and that is equal to, this is nothing but one potential divider circuit. Okay, so it will be equal to R3 divided by R2 plus R3 times V in. Okay, so now my output voltage equation will become 1 plus Rf by R1 times R3 divided by R2 plus R3 into V in. Okay, this is the change. The output voltage in case of non-inverting amplifier when V in is not directly applied but applied through some resistive circuit. So remember always, you need to find out the voltage which is available at this non-inverting terminal, not the supply voltage. If supply voltage is directly available at the non-inverting terminal, in that case my output voltage would be 1 plus Rf by R1 times input voltage. Okay, so this fact will help us to analyze some complex operational amplifier circuit in which non-inverting amplifier is a subpart. Okay, so this is what you remember. Remember that non-inverting amplifier always amplify voltage at its non-inverting terminal. This is the most important, remember, right? Now this is what we have seen in case of amplifier circuits. Okay, but as I have told you, this is the ideal amplifier circuit. Okay, and now whenever we talk about the practical amplifier circuit, at that time there will be some difference. Okay, so we must analyze these practical amplifier circuits. Okay, so we'll start with the basic inverting amplifier circuit first. Okay, so we'll talk about practical inverting amplifier. Okay. Now if we compare our practical inverting operational amplifier with the standard one, that is the ideal operational amplifier, then in that case what is the difference? The first difference is input resistance R in is less than infinite, because practical op amp has some finite input current. So what will happen if my input current is not infinite, or sorry, input resistance is not infinite, then op amp input current will be finite value. Second, open loop voltage gain will also not be equal to infinity. Okay, there will be some definite gain. Say in case of IC 741 we have the value of 2 into 10 raised to 5. And third thing, output resistance will also not be equal to 0. Okay, so we need to consider all these non-idealities while analyzing the inverting amplifier circuit. Okay, so let us try to analyze this practical inverting amplifier circuit. Okay, so we will always deal with the practical inverting amplifier, not the ideal inverting amplifier. Right? So as this is inverting amplifier, we will ground the non-inverting terminal, and to the inverting terminal we will provide some signal. Okay, it may be AC signal, it may be DC signal, but whatever signal we are providing, that signal will get amplified with respect to output voltage. At the output terminal, I will connect one load resistance which is grounded. Okay, so this is my load resistance, this is feedback resistance, and this is forward resistance R1. Okay. And we will be providing positive supply voltage and negative supply voltage to the circuit. Okay, this is my op amp. Now this is terminal A and this is terminal B. Okay, and we are providing some input voltage V in over here. So what will happen whenever we have the practicality? At that time, bias current will always be there. Okay, so here we need to consider the current IB1 and current IB2, which is flowing towards the op amp terminals, input terminals. Okay. Now we have some voltage VB, and here we have some voltage VA which is available. According to virtual short concept, VA will always be equal to VB. Okay, and when we switch on the supply, there will be an input current flow in this particular direction. Okay, so at this terminal A, current gets divided into two parts. Some part of current will flow in this direction and some part of current will flow in this direction. Let us say this current is feedback current IF. Okay, so at this terminal we are going to measure output voltage V0. Right, so this is the typical practical inverting amplifier circuit. Okay, this one is practical inverting amplifier. Okay, now here this resistance RF forms a feedback circuit. Okay, and the amplified as well as inverted output voltage is also applied to the inverting terminal through this feedback resistor RF. Okay, so the polarity of output voltage which is fed back will be opposite to the polarity of the input voltage, and this is the reason why this feedback is known as negative feedback. Okay, so this practical inverting amplifier is also known as voltage shunt feedback amplifier. Okay, this configuration is also known as voltage shunt feedback amplifier. Okay, now why it is called voltage shunt feedback amplifier? See what I am doing, just I will try to redraw this typical circuit. Okay, so we have, okay, right now what I am doing, see non-inverting terminal I have changed. Okay, and it is grounded as we know. Okay, so this is grounded. Okay, and inverting terminal we have supply voltage over here like this, then there is a feedback resistor which is like this. Okay, and here we have load resistor, okay, which is also grounded. Okay, so this is my load resistance RL, this is our feedback resistance RF, this is my forward resistance R1. Apart from this we have positive supply voltage and negative supply voltage given to the circuit. Okay. So here we will have voltage V1 and voltage V2. Current IB1 is flowing over here and current IB2 is flowing in this direction. Okay. Now here you can see the feedback circuit. Okay. This is the one with green dotted line forms the feedback circuit. Okay. And this is my input current IN. Okay. So we have done nothing, just I have redrawn this typical network. Okay. So here with this feedback circuit, you can say we are shunting the voltage, and this is the reason why this configuration is also known as voltage shunt feedback amplifier. Okay. So with this, let us try to derive the expressions for voltage gain, input resistances, output resistances, bandwidth for this practical inverting amplifier circuit. Okay. And it will also explain the effect of negative feedback on various operational amplifier parameters. Okay. So let us start with the finding out the closed loop voltage gain first. Okay. The first parameter which we are going to find out is voltage gain. The closed loop voltage gain. Okay. And this is denoted as A suffix CL. Okay. It is nothing but the ratio of output voltage to input voltage with feedback. Okay. Yeah, remember this. It is nothing but the ratio of output voltage to input voltage with feedback. Okay. So let us try to derive this. Right. So we'll consider this figure. Now here we have node A and node B. Okay. So at node A you can see the current input current get divided into two parts. Okay. So to find out the voltage of this, what we need to apply? We need to apply Kirchhoff's current law. Remember, always we have these two laws, Kirchhoff's voltage law and Kirchhoff's current law. So suppose we have to identify, we have to determine the unknown amount of voltage. At that time, Kirchhoff's current law will help us. And if we want to find out unknown amount of current, then Kirchhoff's voltage law will help us. Okay. So right now we are interested in deriving the unknown amount of voltage. So KCL will help us. So we will apply KCL at node A. Okay. So applying Kirchhoff's current law at node A will give us this equation. I in is equal to IF plus IB2. Okay. Let us go back to the circuit diagram. See, this is my input current IN. It is divided into two parts, IF and IB2. And that is what we have written. IN is equal to IF plus IB2. Now, we know here that the input resistance Rin is not infinite, but it is very large. Okay. And this is the reason why this IB2 will be negligibly small and you can almost neglect it. Okay. So IB2, if we talk about, is negligibly small and can be neglected. Right. So now this equation 1 will become I in is approximately equal to IF. Okay. Now what is I in? If we go back, I in is the current which is flowing between V in and VA. Okay, so I in is equal to V in minus VA divided by R1, and RF is the feedback current which is flowing between A point and output point. So VA minus V0 divided by RF will give us the value of Rin. Okay, so just putting these two values, V in minus VA divided by R1 is equal to VA minus V0 divided by RF. Let us call this equation as equation number 3. Okay. Now we also know the output voltage equation. It is equal to gain times the input voltage, which is nothing but the differential voltage VD. Okay. Remember, recall the equivalent circuit of op-amp. Okay. So from equivalent circuit of operational amplifier, we can write down V0 is equal to AOL times VD. Okay, that is equal to AOL times V1 minus V2. Okay, this is equation number 4. But what is V1? Okay, let us go back to circuit. V1 is the voltage available at this terminal, non-inverting terminal. It is grounded, right? So V1 is equal to 0 as it is grounded. Okay, so V1 here is equal to 0 volt as it is grounded, and according to virtual concept, V2 will be equal to VA. V2 will be equal to VA volt. Okay, therefore what will happen to output voltage V0 equation? V0 is equal to now minus AOL times VA. Okay, so we'll keep this equation and we will put this equation in equation number 3. So in place of V0, let us put this equation. Okay, so substituting this in equation number 3. So we have V in plus V0 by AOL gets divided by R1 equal to minus V0 by AOL minus V0 divided by RF. Okay, so we have put these equations. Now just simplify the terms and try to find out the ratio V0 by V in. Okay, so we will simplify this, become V in RF plus V0 RF by AOL is equal to minus R1 by AOL times V0 minus R1 V0. Therefore, V in RF is equal to minus V0 times R1 by AOL plus R1 plus RF by AOL. Okay. Now, if we talk about this ACL, what is open closed loop gain? Closed loop gain ACL is nothing but the ratio of output voltage by input voltage with feedback. Okay, so we are available with this V0 by V in, right? So ACL will become minus AOL times RF up 1 R1 plus RF plus R1 times AOL. Okay. This is the exact expression for closed loop gain in case of practical inverting amplifier. Okay, so now if we consider ideality, let us unbox this first one. Okay, and this is exact expression for closed loop gain, right? Now ideally, if we think ideally, what is AOL? AOL is very large and it will tend to infinity. Okay, so if we talk about this parameter AOL times R1 will be very much greater than R1 plus RF. Okay, so you can almost neglect this R1 plus RF from this denominator term. Okay, because this R1 times AOL is very much large. Okay, so ACL can now be reduced to AOL times RF divided by AOL times R1. Okay, so here we can neglect this AOL. So finally we are left with RF by R1. Okay, and that is what we have derived, right, in case of ideal condition, right? So closed loop gain is equal to minus RF times R1, and this is the exact expressions which we have derived earlier in case of ideal inverting amplifier, right? So this is true. Okay, so if we consider practical inverting amplifier, then this should be our gain, and if we consider the idealities, then minus RF by R1 will be our gain. Okay, so we will be able to derive some block diagram for this practical inverting amplifier. Okay, so to obtain the block diagram of practical inverting amplifier, it is necessary to represent the current summing junction at the input terminals of an amplifier as a voltage summing junction. Okay, let us try to see. Okay, see, we have input signal V in over here. Okay, and then this input signal gets amplified. Okay, let us say we have some block K, and then there will be one voltage summing signal. Okay, so this voltage will generate the differential voltage Vd, and this differential voltage Vd gets amplified, and we will be able to get output voltage V0. Okay, but we are taking feedback also. Okay, and this feedback network will also have its own gain. Let us say this gain be B. Okay, so V0 we are providing as an feedback input, and that will give us the feedback voltage V. Okay, so this is nothing but the summing point. Okay, in control system theory, you already have gone through the basic block diagram techniques, right? So you know the importance of the summing point, right? So this is my block diagram of practical inverting amplifier. Okay, now let us try to obtain the transfer function. What do you mean by transfer function? Transfer function is nothing but the ratio of output by input, that is V0 by Vin. Okay, so we have to derive this equation. Now here at the summing point, we can write down, okay, at the summing point, we may write down minus V in K minus Vf is equal to Vd. Okay, so Vd times A is equal to V0, and V0 times B is equal to Vf. This is the two equations which we have derived from here. See, the block diagrams are connected in series. So if we talk about V0, V0 will be equal to Vd multiplied by A. And if we talk about Vf, Vf is V0 multiplied by V. Okay, so these three equations are there. Here A is open loop gain. A is open loop gain. B is feedback circuit gain. Remember, B is feedback circuit gain. And K is attenuation factor. K is attenuation factor. Okay. So suppose this is my equation 1, 2 and 3, then equation 2 and 3 can be put in equation 1 and 2, 3 can be put in equation number 2. Okay, so what we will get, Vd is equal to minus V in times K minus Vf into A is equal to V0. Now V0 is equal to, okay, so I will justify this thing, V in times Ka minus V0, Vf is equal to V0B times A is equal to V0. Therefore, V in times Ka will be equal to V0 into 1 plus BA or AB. Okay. So, V0 by V in is equal to minus AK divided by 1 plus BA. Okay. So this is the transfer function of practical inverting amplifier. Okay. And we know the equation, closed loop gain equation. Okay. It is equal to minus A0 L times RF divided by R1 plus RF plus R1 AOL. Just we have derived over here. Okay. So if we consider this equation and divide this equation by some term, okay, I will just redrive this equation. ACL is equal to AOL times RF divided by R1 plus RF plus R1 AOL. Okay, and what we will do, we will divide numerator and denominator by R1 plus RF. Okay, so the closed loop gain will be now be equal to minus AOL times RF by R1 plus RF upon 1 plus R1 times AOL divided by R1 plus R. Okay. So this equation, let us call this equation as equation B and the previous equation as equation A. Okay. What is it? It is V0 by V in, which is nothing but the gain. And here this is also gain. Okay. So these two gains are equal. So we can equate A and B. Okay. So by equating this A and B, what we will get is the closed loop gain is equal to minus AOL times K divided by 1 plus AOL times B. Okay, where A is AOL, which is open forward path gain, B is R1 divided by R1 plus RF, which is feedback path gain, and K is RF by R1 plus RF, which is voltage attenuation factor. Okay, so we have this equation of closed loop. Okay, so here if you consider this parameter AOL times B, okay, AOL into B, it is very much greater than 1, and hence 1 plus AOL times B is approximately equal to AOL times B. Okay, so ultimately ACL is nothing but minus K upon B. What is K? K is equal to RF by R1 plus RF, and B is equal to R1 plus RF by RF. Okay. So this term will get cancelled out, and finally we will be left with minus R1 RF by R1. Okay. This term will get cancelled out, and this is what we require. See, again we are getting the closed loop gain is equal to minus RF by R1. Okay, and this is what we have derived in earlier cases also. Okay, so this block diagram is also true. It is truly representing the practical inverting amplifier. Okay, so this is how analysis is being done in case of operational amplifier. Okay, now we will try to find out the input resistance value also, because we know in case of practical amplifier it is not infinite, okay, but it will have some final value. So in order to do analysis, we must find out the exact value of these input impedances, output impedances also, as well as we will try to find out the frequency range also, which is nothing but the bandwidth. Okay, so for today we will stop here. In the next lecture we will continue with this practical inverting amplifier circuit, and we will try to find out the remaining parameter of the circuit. Okay, if you have any questions regarding today's topic, then you are free to ask.